my interest in this area is every day I wake up, I ask myself a simple question: why am I not dead? And the reason I ask this question is because if you look at the number of cells in you that are you, you are not you. You are something else. What I mean by that, there are more cells in you that are other than you than there are other than you. Your gut is full of bacteria. There are viruses incorporated in almost every cell of your body, and yet, rarely does this cause problems. In addition, we're bombarded from without. We're constantly bombarded by viruses, bacteria, and other things whenever you're exposed to other people or in the environment, and someone sneezes on you. What's interesting is that if you take a room and you were to, say, spray influenza in the room, most people will be fine. Only a small fraction of them will become infected. In fact, even when you deliberately inject influenza into the nose, fewer than half of the people who are exposed come down with disease. What does this mean? Well, what it means is that the biopharmaceutical industry has tended to focus on the people who have the disease and try to design drugs to treat a specific pathogen by targeting molecules that are components of the pathogen. We're interested in the people who are going out the door, who nobody cares about. How come most of those people are immune? And this leads into the concept of innate immunity. Innate immunity is immunity that I will show you in a chart that graphs some of the important facets of innate immunity that does not require prior exposure or antibodies or some such. It is somehow the body has evolved ways of defeating almost all pathogens almost all of the time. And our work focuses on the body's innate immune system and capacity to, by and large, defeat almost every pathogen known. It's a very powerful system, and we know very little about it. And our work, we think, has made some inroads into understanding what is going on in innate immunity. In particular, today I'll talk about our work in HIV, although our work, as mentioned by Les, extends far beyond just HIV, and we'll come to that. What's the problem with HIV and AIDS? Well, you know, it's forgotten but not gone. Worldwide, there are 42 million people living with HIV and AIDS as of 2002, and the WHO compiled this report. And as you can see, the focus is largely in sub-Saharan Africa. The country that's going to have the most AIDS patients predicted in 10 years, believe it or not, is India. Kind of interesting where this is going. New cases from adults of new HIV infections. So per year, 5 million people or 14,000 people per day are infected with HIV. And if untreated, every one of them will die. Annual deaths due to HIV, here we have the United States, is 16,000, worldwide 3 million. The problem will get worse before it gets better, and that's true, not necessarily in the first world, but in the second and third world. For example, here are some predictions in China where the estimates are of an explosion of HIV and AIDS in the very near future. By 2010, we're talking about 10 million infectees. And very little is being done to stop this at this point. So what is the challenge and the unmet need that got us involved in this area? There are 28 antiretroviral and anti-HIV medications on the market currently, and all target HIV-specific molecules. The HIV virus replicates very prodigiously, up to 10 billion with a B, that's not a misprint, this is a Carl Sagan number, times per day in an infected person. And the virus has a very large error rate associated with its replication, which results in large numbers of mutations. And for those of us who believe in evolution and natural selection, this generates a lot of resistance. In fact, 20 to 30% of new HIV infections in this country are with a virus that has evidence of resistance to at least one of the antiretroviral medications currently approved. Bottom line is we are running out of time. It's only a matter of time before the virus outsmarts every drug in the armamentarium. So what is this leading to? New approaches are needed. What is this thing called innate immunity, and why is it important? Because our approach is fundamentally different. It's an approach to antiretroviral medications that is unlike any that is out there currently. Only about 1 in 300 persons exposed to HIV-infected blood by needle stick injury becomes infected. And most people, of course, and researchers focus on that one person who is unlucky enough to get HIV. We, of course, are more interested in those 299 who didn't get infected and say, well, what's up with that? This is also true for all other infectious diseases of which I am aware. TB, for example, despite the fact there are billions, as in 2 billion people in the world infected with TB, the number of people who are infected probably far underrepresents the number of people who are exposed and have innate immunity to it. This little one, this slide takes a little second to boot up because I think it makes a graphic description of what I just said, because I like very graphic type pictures. This is Iron Man, although it's currently #1 in the box office. I'm kind of a comic book fanatic. Here's HIV, and this is actually, I actually have 300 little Iron Men standing around here, showing that if you expose 300 people to this virus by needle stick, which is a pretty good way to get the infection, only one gets infected. So what is the secret of immunity, innate immunity, of these people who are not infected? In other words, it seems that evolution has solved a problem that we are spending a lot of money trying to figure out again. What is innate immunity? It's a response to pathogens with an operational definition, or a definition based on its characteristics. Rapid onset after pathogen exposure, that is to say, it operates within minutes to hours. Minute-to-minute control of pathogenicity, non-localized, functions everywhere in the body, not restricted to any particular location. There's no requirement for prior exposure to the pathogen. It is, in a sense, hardwired into the body. Its response is to broad-spectrum molecular components, often called PAMPs in the literature. It's a jargon term. It means pathogen-associated molecular patterns. There are certain elements, cells, molecules in the body that represent broad-spectrum patterns of organisms, and it's designed to defeat these organisms. There is no memory function, that is to say there are no antibodies or secondary response due to a vaccine. This is a non-vaccine type of approach. And I want to point out the recent rather spectacular failures of all the AIDS vaccinations should give us pause and make us think that another approach seems to be more fruitful. What are the components of innate immunity? What's the hardware of innate immunity? Well, some of them are very strikingly non-cosmic. Skin. Cells lining the GI respiratory tract, cilia, flow. Things like urine can flush out pathogens. Very simple ideas. Normal flora, the bugs that inhabit your skin and inside your gut, crowd out the pathogens. There are some anti-pathogen molecules, complement, defenses, lysozyme, coagulation factors, and many others. These are just some of the representational list here. And cells participate in innate immunity. Polymorphonuclear leukocytes, the components of pus, monocytes, macrophages, and NK cells. These are cells which do not need prior exposure to the pathogen to defeat a pathogen. Comparison of innate versus acquired. Evolution, the innate immune system is far older than the acquired immune system. Timing, as I pointed out, is very rapid. This is what's accounting for minute-to-minute defense against all the bugs that are bombarding you as we speak. Acquired immunity takes 4 days to develop an antibody-type response. Targets include molecular patterns. Targets here are super-specific molecular fragments, or epitopes, as the jargon term says. Genetic rearrangement, no. For acquired immunity, yes. You have recombinase and enzymes that make receptors in multiple millions, billions of combinations that put them together to generate all these kinds of recognition patterns that can generate antibodies and cytotoxic T lymphocyte receptors. What are the effectors? Barriers, peptides, monocytic cells, and other cells. Antibodies, B cells, and T cells for the acquired immune response. There are no reports demonstrating the capacity to culture HIV in whole blood. Think about what this means for a moment. This is a bug that replicates up to 10 billion times per day in a whole human being, and never, except once, has anybody cultured this virus in blood. There is something in blood that inhibits this virus 100%, which is 100% safe, 100% natural, 100% effective, and there's no possibility of mutation-induced resistance. Just think about that. The risk of contracting HIV, as I said before, following needle stick exposure is small. Those of us who work in this area are like this idea because we get needle stick exposures happening all the time, at least in the clinical service. So what is the basis of this? What is the hardware of this innate immunity? What is it in blood in particular that is floating around protecting people almost all the time against HIV infection? And without going into all the details, I can't do that in a 15-minute discussion. We focus on a molecule called alpha-1 antitrypsin, something which people in this room may have heard of. Let's talk very briefly about what AAT is. It's a molecule floating around in blood. In fact, depending on how you count numbers, it is the second or third most abundant protein in serum, very abundant. Molecular weight about, half the size of an antibody. This number of amino acids, about 100 different flavors or alleles. The normal concentrations are quite high in the milligram per ml range. Let's talk about the science of this molecule, HIV antitrypsin, as a putative or candidate innate immune mediator of protection against HIV. We found that AAT inhibits HIV up to 100% in every known in vitro assay of HIV replication. There's several unique advantages to this approach. Let's talk a little bit about drug discovery and development now. First of all, it's a natural molecule with more than 20-year record of safety, already FDA approved for separate indication. There are people in the world, about 100,000 in America, who have a deficiency of alpha-1 antitrypsin. And these people are treated with infusions of antitrypsin intravenously, and that accounts for the 20-year record of near perfect safety for this drug being given to those patients. If there's time, we can discuss about whether or not there's a relationship between antitrypsin deficiency and HIV. This is a very important part B. Let's assume that we can combat HIV by an antitrypsin or innate immune-mediated therapy. What's unique about this, and what separates it from all other therapies, is that there's no threat of mutation-induced resistance. Why? Because we target the host. See, most viruses, all viruses I'm aware of, require the appropriation or hijacking of host molecules in order to replicate. In a sense, a virus is a computer virus that needs a hard drive to replicate. No hard drive, no replication. In the same way, if we can deny access of HIV to the molecules it needs to replicate, then we can shut down HIV in a way that it can never get around, because we don't target the virus. We target the host molecules that the virus requires to replicate. Data. Let's talk about U1 cells. It's a cell that has HIV incorporated into the genome like a chronic infection, and if you stimulate it with any one of a number of inducers, you pump out lots of HIV, and you can measure it by P24 antigen. Representation of some of our data. These are these U1 cells again, and the control cells, cultured medium and low, make a small amount of HIV that we measure by P24 antigen. If you stimulate the cells with a molecule called IL-18, and we've used several others, but I'm just presenting IL-18 as a convenient stimulus, you get a large increase in HIV replication. On the other hand, if you add IL-18 in the presence of antitrypsin, you see a dose-dependent and 100% suppression of HIV replication. Regardless of stimulus, we have found this to be the case. And even if we use virus that's resistant to multiple drugs, we still find the same kind of suppression. I'm going to jump ahead to an experiment that we did. That's the first report I'm aware of propagation of any virus in whole blood. Remember I said one time it's been done, and this is the time. This is whole blood from healthy volunteers, and we added a pathogenic HIV virus to the blood after we took it out of the patients, the volunteers. And 14 of them dumped the virus in and measured it, P24 antigen, and found a small amount. If you wait 4 days, you see a minuscule increase in HIV, basically recapitulating what had been observed before, which is this virus cannot replicate in whole human blood. On the other hand, if we obtain blood from 5 special people, these special people have a genetic deficiency of antitrypsin. They're perfectly normal otherwise, but they don't make alpha-1 antitrypsin. In these people, you see a marked increase in HIV replication in the whole human blood, demonstrating beyond all doubt that antitrypsin is likely an innate immune mediator of HIV replication in whole human blood. This is the first demonstration I'm aware of any laboratory replicating any virus in whole blood. These are very recent data where we actually measured alpha-1 antitrypsin levels in AIDS patients compared to controls, or should I say HIV-infected persons. We wanted to know what would happen to the relationship between alpha-1 levels and infection with HIV. Here are control people, and we used a lot of patients here, 52 healthy controls in this case, and here are the numbers, and here's the median represented by the white bar, and here's the level of antitrypsin in milligrams per ml. In contrast, if you measure 102 HIV-infected patients, you see a significant P equals 0.006, very, very significant reduction in the amount of antitrypsin. This is quite unique because almost every other disease that we're aware of, antitrypsin levels are increased in the presence of disease, not reduced. There appears, therefore, to be a relationship between reduced alpha-1 antitrypsin levels and infection with HIV. Now, what causes what, we cannot say. My guess, if I were to make one, is I believe the HIV is causing this. I do not believe people with low levels of HIV, low levels of antitrypsin, happen to be getting HIV infection, although that could be the case. There's one case report published that strongly implies that. So this clearly shows in the clinical setting that there's an association between low HIV levels and low antitrypsin levels and infection with this virus. What's our proposal? What are we going to do? Where are we going with this? Well, we're going to administer an FDA-approved drug called alpha-1 antitrypsin intravenously as a single dose to 7 HIV-infected persons with actively replicating virus. Then we're going to assess the AAT effect on the HIV viral load in blood that will be measured serially for 1 week after infusion. HIV replicates so quickly that if you were to shut it down, you can detect the difference in the blood in virus by viral load in about a day. So it's very, very quick. So here's the design of our experiment. We have our subjects who are HIV infected with a viral load over 3,000. No antiretroviral therapy because we wanted no interference with drugs and compliance with the drugs, and informed consent. Intervention, a single infusion of human alpha antitrypsin at 60 milligrams per kilogram. And we're going to measure as an outcome the viral load. We're going to hope that the viral load is suppressed. And we're going to measure serum AAT concentrations. This will also, by the way, be the first, will be a unique study. It will be the first time normal, healthy people have gotten an infusion of antitrypsin. In fact, we have already obtained FDA approval to do this because the drug is that safe. Advantages, and I believe this is the last slide. What are the advantages of this proposal compared to some other approaches for HIV therapy? Well, the need for improved antiretroviral therapies is immediate, as I pointed out, because of resistance. No possibility of mutation-use resistance. And I put that in sort of bold strokes, and we anticipate that'll be the case, but who knows when we do the experiment. It should be synergistic with currently available antiretroviral drugs because they're different mechanisms of action. We don't think that we're going to cure AIDS here, but we may have an approach or a drug that can work in concert with other antiretrovirals to achieve greater control of HIV in patients. First generation drug candidate, antitrypsin, is ready for testing on the shelf. There's a prospect for next generation drug discovery and development because we found out some important molecular mechanisms of how this drug, antitrypsin, suppresses HIV. And we're already working on the next generation of small molecule inhibitors of the relevant targets. And the relative ease of FDA approval, FDA fast tracking for HIV drugs, and the approval of antiretrovirals is based on surrogate markers. So you don't have to look for life and death. All you have to show is substantial viral load reductions. So it's an attractive biopharmaceutical drug discovery and development candidate. And that's the end.